Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture on proportional solenoid pilot operated two stage pressure relief valve. This lecture is the first part of this topic. Now, we know about the pressure relief valve, then two stage means there is main stage and pilot stage. Pilot stage can be compared with direct pressure relief valve, and when that stage is associated with main stage, then this must be operated by something and it is called pilot operated, and in this case operation of that pilot stage is done by proportional solenoid. Now, proportional solenoid is in comparison to the ordinary solenoid is that in this case the input to the solenoid is either current or voltage, and then due to that it is input is in such a way the output will be linear to the current or voltage what is the input. Now, let us look into the constructional feature of this valve. In this diagram what I have shown one sectional view of the valve. In this case in this view this is the main stage and this is the input side, flow input side. If we look into the figure at the top, which is schematic diagram, the main system line is here and this is connected, this valve is connected to the main system. Now, this is the drain to the tank. So, while on relief it will come out from this path and it will go to the tank. Now, the upper part here, this is the pilot stage. In pilot stage what we find? We find a poppet, this conical poppet, and this is sitting on a hole. So, this must be a variable orifice, and then the operation can be described like this. Now, this spool is being driven by the proportional solenoid, and this drive force is being transmitted through a spring, not directly. This poppet is not directly connected to the solenoid spool, it is connected through a spring. Now, this is the input for the current or voltage whatever it might be, this is input to the proportional solenoid. So, this will move, this movement may not be linear although output will be linear, but this will move the right and left due to depending on the input here, and this is the LVDT to record the position of this spool. So, for this portion it is a closed loop, we can say that one current is there, then the signal is going over there and then again this is being corrected. This portion is closed loop, the other portion is maybe closed loop through a computer or microprocessor, we can make it closed loop. Now, how it is being operated? If we look into this view, then we should compare the main portion, the main stage portion is the bottom portion here, whereas the pilot stage is the top portion here. Now, in between that there is another portion which is maximum pressure adjustment setting. This means that this valve, depending on the solenoid input, this can be operated for a range. Say it can be operated from 0 to 20 megapascal, but due to the over precaution or for more safety, what we can do, knowing the system pressure requirement, we can set the pressure here. Say this is 10 megapascal or 12 megapascals. Then at 12 megapascal, this all flow will go through this. So, although this can be operated up to 20 megapascal, but due to setting maximum pressure adjustment over here for the 12 megapascal, this oil will be relieved through this valve, it will not come to this stage. However, in many cases this part is not there, first thing. Second thing, this is again we can say the another pressure relief valve. So, for the studying the pressure solenoid pilot operated pressure relief valve, we shall not consider this part. So, we have consider only the bottom, the main stage, and top, the solenoid part. Now, what we look here, that this is the main flow, then the flow is coming over here. Say it is we will operate at 10 megapascal up to maximum, that means up to 10 megapascal pressure will be there, but this will not open. So, then this oil will be connected to this, okay. It will be connected to this path. Now, when this oil is going through this path, if this does not open, how it will be open? How it will open? When the pressure here sufficient to open this poppet, only then it will open. Now, unless the pressure is not increased to that level, there will be no flow. So, there will be no flow through this passage, although this will be filled in with the pressurized oil. This means that whatever pressure here, the same pressure will be here also. You can see this path, it will be here also, here, everywhere the pressure will be same, and this will not open. Now, this is we are operating at 10 megapascal range, say after 10 megapascal this will be there. So, what we can do, we can set this current for 10 megapascal. In fact, this proportional solenoid is there, that this pressure relief valve can be operated within that range for any pressure. That signal, instead of in ordinary system where we set the pressure by adjusting the knob and we leave the system like this. In this case, through the current signal we can, or voltage signal, we can operate any time for any pressure within that limit. Okay. It might be computerized, it might be manual also, or maybe through a microprocessor. Okay. Now, let us consider this signal what we have given in such a way that it should open at 10 megapascal. This means that at 10 megapascal this will open. Now, once this opens, the flow will start. This flow will go like this, and then through this is blocked. So, through this passage it will go to the drain. Now, this passage is also blocked. Okay. Now, as flow begins, then definitely there are so many orifices. So, there will be pressure drop. So, up to pilot stage, how many orifice we find? One orifice A, another orifice B, and then here there is the variable orifice. These are the fixed orifice. A and B are the fixed orifice and D is the variable orifice here. And after this pilot stage also there is another orifice. in this directions, and the oil is being transmitted through this main spool chamber also through an orifice C. Now, when flow begins, then there will be pressure drop. Now, as there is a pressure drop, the same pressure will come over here. So, if we think of the force balance, this side the full pressure, this side the reduced pressure plus the spring force. So, depending on the flow at one point, these two force will be less than this force, then this will open and oil will go out, and that will depend on how much setting we are doing through this proportional solenoid. And as you know, due to this differential pressure, this will remain stable for a longer time to bypass the oil. That means no chattering. Otherwise, normal case you will find that here there will be pressure drop, and if it opens too much, pressure here and pressure here will be same, that means it will be almost 0 pressure, and but this side is the pressure is automatically there. If it is 0 pressure, try to be 0 pressure, then again it will be closed like that. But due to this balance, there will be an orifice effect, a small orifice will open. So, maintaining the pressure here up to the system pressure, say it is 10 megapascal, the oil will pass until this pressure reduced to close this valve. Okay. So, this is the basic operations. Now, here again I would tell that we have seen one orifice A here, another orifice B before this pilot stage. That means, if I think the same oil is flowing through this pilot stage, at least there are 2 orifices. Now, apart from that, what we find that there is also some fixed resistances, fixed orifices is also there. These orifices can be replaced, whereas this cannot be replaced. Now, here I shall discuss later, but here what we find that there we find a spring. I have already mentioned the force is being transmitted through the spring, not directly through a solid stem, whereas this spring is very soft spring, and this is just to keep this poppet in positions. It has a role, as there is a spring, definitely it is having a stiffness. So, we have to consider this stiffness also for the functioning, but the stiffness of this spring is much less in comparison to the stiffness of this spring, and but this is required, otherwise this poppet may not be in proper position, it may start malfunctioning. Okay. The functional feature already I have described. Now, this solenoid already mentioned, it has a built-in linear variable displacement transducer, which is called LVDT. This LVDT transducer is there. It monitors the position of this spool, and for this it is a closed loop. This valve, whether it is closed loop or open loop, depends on how we connect this control over there, the driving current which we are supplying. However, the position transducing is closed loop. Okay. Now, another important point, the hydraulic parts remained more or less same as in conventional 2-stage pressure relief valve, which is normally called as PRV. Actually, there is some confusion in this terminology. Normally, we call pilot operated pressure relief valve POPRV. O is small, all other capital. The next lecture I will describe that also. So, here again it is solenoid operated. So, for that no this abbreviation term is there. Normal course we call proportional PRV, simply call it, but once it is a proportional PRV, means it will be POPRV proportional pilot operated pressure relief valve, that you should remember. Now, another important aspect I would like to mention in comparison to the servo valve, the solenoid valve, the proportional solenoid valve, the accuracy of the all components is not that important what we require for the servo valve. In case of servo valve, it is completely closed loop, and there it starts malfunctioning, then whole valve is to be rejected. Whereas, in this case it can be made closed loop through the main drive, that is it might be a, there is a card, of course, here is a card is there, and then it might be a microprocessor, it might be manual, it might be a computer, but there we can set a program so that it can correct all those error. Of course, it should be within a limit. So, therefore, these valves are less expensive in comparison to the servo valves, but we should look into the purpose. Say for example, if you think of operating a missiles, we have to perhaps still go for a servo valve, but it is also possible we can put a proportional valve there, very accurate proportional valve there, and it will also can perform the same thing, but as you know, in both the cases everything will be destroyed, everything will be destroyed. This is just for single applications. Now, if we look into the accuracy, servo valve, perhaps if say missile, if you have targeted a point, then it might be within say 1 meter circle, the missile will hit there if it functions properly. In case of proportional valve, probably that area will be more. That does not mean it will not hit that point, it might be instead of that it may hit the point, whereas say same thing is using a proportional valve, it may hit the target, whereas a servo valve may be half meter area, but still for more accuracy we are going to use this servo valve. Now, proportional valve, so where is the function of this proportional valve? Where we need a longer life by compensating the accuracy a little bit, we should go for the proportional control valve. In that way, I would say the in between the servo valve and ordinary valve, the proportional valve is maybe the optimum from application point of view, and in many cases where we can go for a higher cost, a little higher cost, then even the ordinary valves are being replaced by the proportional valve for better performance. Say in where we use the automation like that. Okay. Now, the orifice A and B are considered as two resistances placed in the series in order to achieve the required optimum pressure drop before the pilot stage. I would say for the same valve, if you change these two orifices, then the range of this operation will change. Suppose you have used A and B orifice with a particular diameter, then you find for 0 to 10 voltage or maybe current, 0 to 10 currents, it is not, it is the milli ampere, it is not in the range of ampere. Within that range, suppose it is working for 0 to 10 megapascals, but if you change this orifice, you may find that this will, depending on the restriction here, it may change say 0 to 5 or maybe for higher, it is like that. Now, we will predict, we will try to predict the theoretically what will be the steady state displacement of the pilot stage poppet of this valve. Now, establishing the relationship between the driving force an input current to the solenoid. In this case we have considered the current is the input current to the solenoid. Based on experimental results, an empirical relations between the above mentioned parameter is proposed. Now, I would like to say this in the control, what we will try to do, suppose we are using a computer, then what we will try to do? We will try to estimate how much current is required to achieve the desired pressure setting. Then if we can have some linear function or maybe empirical relations, it is linear. So, that empirical relations we can use and very fast we can calculate how much current will be required, and then that can be again given as a input. So, what we did, I mean this was an real study was conducted here in IIT Kharagpur. Then what was done, we wanted to establish, we tried to establish that relations. This will make us understanding how this valve can be analyzed both for the design as well for the performances. Now, a complete mathematical model to describe a PRV requires first of all a comprehensive study of all orifices characteristics, flow and force interactions of the pilot stage, flow and force interactions of the main stage, and valve geometry, that we should know. Now, I would like to say that if you go to the market, you will be able to buy one proportional solenoid valve. The characteristics is given and it is available that what should be the current input for the pressure output, pressure range. So, this curve, what is the curve is given, that either you can program or you can feed on in a computer on the data basis. You can make a data table and that can be used for the control. And usually the supplier, they have their own control features, so that you directly you can use. And nowadays you will find there are many controller is available which can be given, say we need say 1 micro milliampere to 10 milliampere. So, you can have a programmer that you can feed, and as you know that what will be the output. So, you can program that easily and you can use this. But once you are thinking of designing such a valve, then in that case you have to know all such characteristics, and we have studied this. So, we shall explain how it is really functioning. Now, first of all we shall look into the orifice characteristics. Now, again coming back to this valve, then A, B, C, E, these 4 orifices apparently it is we should call the short tube orifices. Now, in broadly we should say this valve will comprises of 2 type orifice. One is that fixed area 1, 2, 3, 4, the fixed area orifice, and the other is variable area. This is one variable area here, another variable area is there. 2 intermediate orifices before and one after the pilot stage poppet are fixed area orifices, say 1, 2 and this 3, these 2 before the pilot stage and 3 after the pilot stage are the fixed area orifices. On the other hand, flow areas of the pilot stage poppet and main stage spool are treated as variable area orifices, which I have explained already. Flow pressure characteristics of each orifices is established through modeling. We can establish this through a mathematical modeling, and then it can be supported by the experiment. Now, damping orifice, this orifice is called damping orifice, orifice C has no role to play on steady state performance. This orifice only when there is the transient conditions, the dynamic conditions comes here, then this oil flow through this orifice, it is in the reversible flow occurs, and that helps in damping the motion of this main poppet. If we remove this, then you will find it will take much more time to stabilize. However, this has no role on steady state performance. So, we have not studied here in this analysis. Now, flow pressure relationship for the fixed area orifices, again we will consider A and B. The orifice is considered as a cylindrical hole with a diverging area in the downstream. Actually, these orifices are like that, almost straight hole is there, but at this side, I mean towards the downstream side, this is upstream. If the flow is going like this is upstream, this is downstream, a slight divergent is there. Now, the flow pattern in such type of orifices suggests the flow and pressure drop relationship as follows. This is the general equations. However, these are known already, we know A is the orifice of this, del P is the pressure drop, and C D is the coefficient of discharge. So, these equations is already known to us. So, we can use these equations for this orifice analysis also. Now, the flow through the pilot stage of the pressure relief valve is very low. It is 2.5 into 10 to the power minus 5 meter cube per second for pressure up to 12 megapascal. Okay. Therefore, CD as reported by Listerwich is expressed as 1 by CD square 64 into L by D divided by RE plus a factor K. Now, here I would like to say that we have already studied that how to find out the CD, and there are also von Mises proposal that how we can calculate, and as I told, in most of the cases we may consider that it can be taken as 0.6, close to that 0.611 precisely we can take those, but it has been found that in this type of valve, if we consider that exactly that one, that will not fit. Rather, we should follow some more refined formula to estimate the CD. Now, in 1965, long back, this is about 45 to 50 years back, about 50 years back, Listerwich, he proposed that this is more suitable, but this he established using the experiments. Through some experiments he proposed this one, and we have also examined and we found that this is really suitable for finding out the orifice characteristics here. L is the length of the orifice, this length, and D is the diameter of the orifice. This is in the range of 0.5 millimeter or even less. RE is the Reynolds number, we have already known. L by D of the orifice varies from 1.5 to 10. Say this is 0.5 millimeter, then L will be maximum 5 millimeter. If it is 0.5, then it will be for the maximum value 5 millimeter, whereas as well this might be 1.5. This means how much? 0.5 into 1.5, it will be 7.75. So, 0.75 is the length of this orifice, it might be like this, of this range. Now, again I have not specified the what is the capacity of this pressure relief valve, what is the physical size. Maybe next lecture I will give a physical size of that, but this is we have considered a only particular valve. It is about 30-40 liters per minute maximum flow. Now, K is a constant. The value of K is evaluated from the above equation, knowing the value of C D from experiments. So, what we have done here, we have found out the C D value from the experiments, and then we find out evaluated the value of K. Now, in determining C D, an experimental technique is adopted. Instead of detaching the orifices from the valve, pressure drop across the respective orifice are measured for a wide range of pressure setting. You see, if we use this orifice separately, we can, it is possible that a test rig can be made and there the orifice can be put and we can find out its CD. But instead of that, we have used all the orifices in their positions and then we have measured pressure. How? If you remember, it is here in this figure that there is a place for maximum pressure setting. We have removed this. Instead of that, we have put a simple block here with these holes, and here is the pressure tapping. So, we put several pressure transducer to record the pressure here, and for the flow measurement here, if we at steady state condition no flow is here. So, flow path is only one path, it is going over there. So, a flow transducer was there. Okay. So, this means that what we did, we measured the pressure drop over each and every orifices and we measured the total flow through all these orifices. So, the position of the pressure measuring probe are shown in this figure. Now, this experimental setup was like that. This is the valve what we used here. This is the Denison valve. I will give the specification next day. Now, here are the pressure transducer. This is the solenoid we have shown, LVDT and solenoid is here, and pressure transducer one is here, one what we can see, one is here, another is here, probably another is here. So, everywhere we put pressure transducer, okay. And here on the detail line, the drain line, we put a flow transducer. This is a turbine type flow transducer, as far I remember. Now, so what we find, these are the orifice, these we marked and these are the pressure transducer, and then a range of input voltage from 3 to 9 volts is applied to the proportional solenoid through its amplifier drive card. Now, here I would like to say that in our case 3 to 9 volt was the input, but through a drive card the output of the drive card was the current, and then that current was driving these solenoids. Okay. The pump has a capacity of 2.5 into 10 to the power minus 3 meter cube per second. This is also not very high, because we ultimately we blocked this one, and through this we just measured the flow through this path, no flow through this path. Okay. The pressure is varied from 0 to 12 megapascal, and we observe the drain flow through the pilot orifice. Here it was 1.67 to 10 to the power minus 5 to 2.5 to 10 to the power minus 5 meter cube per second for this pressure range. Now, I would like to say at 0 pressure there was no flow definitely, but we varied from 0 to 12 megapascals, then definitely at certain pressure this opened, and for this range it was 1.67 to 2.5 into 10 to the power minus 5 the flow. Now, here again I would like to mention, if you the voltage we have seen the 3 to 9, that means up to 3 voltage almost no response is there. Again from 3 to 9 voltage you may find only maybe from 4 to 8 voltage the output is linear. So, that is the application range of this valve, that is specified. The manufacturer will specify also experimentally we have found the similar results. The main relief port was kept blocked. If you look into this, this was kept blocked, so that all the flow goes through this. Now, keep in mind that if we keep this is blocked, then this will not function. So, that means this flow will come, it will try to open, but this will not function. So, all the oil will go through this, and our purpose of finding the CD will be achieved. Now, A, B, C etc. we are dismantled from the valve and measured their dimensions, everything we are measured. Pressure drop across the orifice B and E, you see that across the B and E flow rates are plotted in this figure. If we look into this, this is the orifice E and this is the orifice B. Okay. Now, here one interesting point is that we found that E is having a different dimensions than B. However, A was having the same dimension what in B. However, A zone, at the A zone, not A orifice, we are measuring pressure here. So, this is the pressure gauge and we have a pressure gauge here. That means, pressure here and pressure you can say here. These two pressure we are measuring, but for that it showed different characteristics, although the dimension of A and B is same. So, definitely we had to find out the characteristics of these zones separately. Now, for that it was calculated that K is coming, that equation, if you remember the equation, that K is coming 1, whereas in that case K was coming 0.65. Now, once the K is found out, then this equation can be used, and using this K and that formula, these are experimental data. You can see this line was coming like this. If you plot that formula what we used, then the line will be like this. Now, next here I have given the written this what are the values of K. here I have mentioned that as measured that A and B orifices are equal in size. However, the experimental results show the pressure drop across orifice zone A here is greater than that across orifice B. That means, here it was more pressure drop. This means that there is more restrictions. I would like to mention there is no way to verify what is there. Although you see this construction wise, here there was a hole, but that hole was blocked, and neither we removed that block, but we could not remove this one. We could not really find what is there inside, but definitely there was an restriction. So, this portion was characterized together considering A and whatever restrictions B is there. Now, if we look into the orifice A, then this is the characteristics of the orifice A, or rather we should say orifice A zone. Whereas, if we put K, which is for K is equal to 1, which is for orifice B, its characteristics was something like this. Okay. Now, if we put orifice A only, then this will be same as like this, whereas orifice A and actual additional restrictor, this was showing like this. This characteristics was showing like this, and from where we again calculated that K loss came to 6.0. Now, the question is that, say for example, here we are getting 0.65, whereas here we are getting the 6, then why we did not use the same thing? Probably reason is that this gives better performance. That means, one small and another variable, or variable means we can replace this with this, probably the better performance can be achieved. And moreover, if you look into this, this is very flat type characteristics of when we combine these two together, although the K factor becoming the same. Now, for that again this equation is like this, and for this one we can have this equation like this. Okay. So, interchanging the orifice A and B, what we did to confirm that this zone, the losses will be more or less same, and as we have measured these two orifices are same, what we did, we replaced this orifice, and but again conducted the experiment, and we found that the results are same. So, this confirmed two things. One is that orifice A and B are same. Second thing is that even after interchanging, the performance is same. So, this confirmed that what we have derived, estimated, these are acceptable for this valve analysis. Now, average value of K for orifice A is also considered as 1, and the reason of measured extra losses at A is attributed to bend accompanied by the convergent divergent narrow passage after orifice A. Hence, for accurate modeling, these additional losses are taken into account. This additional pressure loss can be expressed as with this formula, K loss half rho Q d A con that area of that restriction to the power squared. What we could do, we measured the area by putting a wear gauge. Different size wear was put there, only the diameter was measured, and we found that if we use this formula, this is we have developed empirical formula, then with this loss factor pressure loss can be calculated, estimated. This is not exactly experimentally, but this can be also calculated. Now, here again I would like to mention, in all such cases normally through this theoretical formulation we can arrive into a value very close to the actual value, and therefore transducer and controller, their job is that getting this value close to that, further refinement is done by the controller itself. This I have described, and then K loss already I have shown that, and we can take this value 6, and the combined pressure drop across the orifice A and the bend can now be expressed as with these equations. So, we can use these equations for the estimation of the pressure drop. Now, as I told, this we measured in that way, but this probably manufacturers they can have better dimensions. So, maybe this formula further can be modified to have these results. Now, I would like to say it is not easy to remember all such formula, this is empirical relations. So, in this case, so suppose if you would like to use this valve and you would like to estimate what are the values and etc., in that case you should have in your hand to calculate all these values. Now, from equation 2 it can be shown that K is independent of the orifice diameter. This is another thing, that K is not dependent on the diameter, it is dependent on the length. This means that orifices having same length should have the same value of K. This is verified experimentally using orifices of same length, but different diameters. We further conduct an experiment by using those orifice, changing the diameter of the hole, keeping the length same, and we found this K value is coming same. So, that again proved this what the formula we have derived that can be used for estimating the orifice characteristics. In the considered PRV, all the fixed area orifices except E have the equal length and hence same value of K. E means which is after the pilot stage to the drain. Now, we shall consider the variable area orifices. Now, in this I am showing this value. So, variable area means here D and the main spool. Okay. So, D is the pilot stage and this is the main stage. But if you look into this construction of this, here this angle is much more higher than this angle. So, definitely with a small displacements the area increase in the area will be much higher than this. So, definitely these will have the CD, particularly if the coefficient of discharge will have different values. We will look into this. Orifice areas at one main stage, that is variable, and pilot stage are functions of respective poppet displacement. So, we have to develop this formula knowing the how much is the poppet is displaced, poppet angle, this angle is called phi, and then the bore diameter D. What is the this bore diameter here and what is the bore diameter there. Then main stage, you can see this, I have mentioned this all this angle, this is the main stage for which we can write down this formula, and similarly for pilot stage we can write down this formula. This formula is same, only this subscripts, that S is for the main stage and P is this for pilot stage, but you should remember these two angles are different. So, definitely nature of variation of this area with the stroke definitely, or stroke or displacement will be different. Now, flow pressure relationship variable orifice main stage, it can be written in this form. The CQ is the flow coefficient. Now, here instead of coefficient of discharge, we call it flow coefficients, and CQ can be written in this form, where RE is the Reynolds number 0.42 like this. Now, this is also established experimentally, but if we now compare with the von Mises model, then CQ is found to be 0.83 from the result of von Mises, because the angle here is less, 0.83, about 0.83, and this you can calculate, this will be close to this, but not exactly same. Then what we find, that von Mises he proposed in 1917, according to him this would be the coefficient of discharge, what we have given is the flow coefficient, whereas in such type of valve normally we find a result like this. So, Takenaka, a Japanese scientist, in 1968 he proposed this formula, and so flow coefficient, this value can be calculated using this formula. Okay. Now, this variation may be attributed to the difference in poppet geometries used by von Mises. This is one point, and second point, he did it for inviscid fluids, and whereas this in this case all the fluids will be viscous. So, what we did, we through the experiment we found that this formula holds good for this type of valve, this type of poppet, the mains poppet. But this is again I would say this is an empirical relations, this depends on what the geometry we are using. So, for a particular valve this formula will be a particular formula. Okay. Maybe if you change this angle, this might be some, this coefficient will be something different. Now, for the pilot stage similarly this formula can be used, and it is called laminar flow constant, and this is the kinetic viscosity, sorry, not kinetic, kinematic viscosity of the oil. Now, in this case I think here I have made a mistake here, 1/8, this relation will be more or less same, and he also proposed this formula for this one, this formula, but in this case as you see for the pilot stage this curve is different from the main stage. In this case this angle is very low. However, this also experimentally found is suitable for this proportional valve. So, this definitely dependent on the Reynolds number and this angle. Okay, but one thing is sure that these two types of poppets are used in proportional solenoid valve, and if we would like to design a valve like this, then we can use this formula and directly we can arrive into this, say we can develop the control feature also using this formula. Now, the flow equation for the pilot stage, after incorporating the functional relationship of the flow coefficient with Reynolds number yields, if we use all such formula, then we can put in this form, and the flow coefficient of the pilot stage Cp is expressed in terms of eta and other parameters as this. We can use this formula then. Okay. So, now we can use this formula to flow through this pilot. Now, steady state flow forces model for both pilot stage and main stage, the control volume approach is adopted. Now, we have to find out the flow forces. So, main stage flow forces can be expressed like this. This is again using the flow force equation, we have to arrive into that, but I think we need to explain this in a little better way. So, maybe we shall continue in the next day. Now, pilot stage force balance can be achieved by this. This is the pressure force and this is the driving force. And this equation can be written in this form. This F d r is the driving force. Here what we find the auxiliary spring force and then flow force and this pressure force. These three forces are flow force, spring force and the pressure force. Okay. Now, the pressure force is created due to the pressure difference. So, if we know the pressure difference, we can estimate what will be the force, and then knowing this area we can calculate also the flow force. So, this force directly given by this formula, and then spring force, this was experimentally measured, that the considering the initial compression is this much, this formula can be written as like this. At this is the displacement at 0 positions and this is the actual displacement, and from there we can find out what will be the spring force there. Then to find out this force also, what was usually for a valve, what is done, say calculating all such meticulous things, you may not find exactly what will be the force. Best thing, we can go for experiment and we can see this how much really force is there. So, what we did, that the required forces in the left hand side of the equations can directly found by the driving force, how much we are putting here. Okay. It is equivalent from the measurements of the pressure drop P c and P d and the flow rate is Q d. The calculation of the poppet displacement Y p using this equation 10 now can be achieved. So, this we experimentally find out, flow was measured, this pressure drop was also measured. So, what could be established, that is the what will be the displacement for various pressure drop. Maybe with the pressure drop this is related. So, once the flow is known and this data which we have examined earlier, from there we could have make a estimate what will be the Y p there, displacement there. Ultimately, this formula was developed. This is an empirical relations, but this is in terms of the I input current. Once you just directly substitute the input current, then you can calculate what will be the driving force there. Now, from the plot, the driving force is expressed in terms of current as the same formula I have written here. So, this means that if this formula is given for a current, we can find out what will be the force. Once the force is known, then we can find out that pressure drop, and from there we can estimate at what pressure it is working. Now, main stage force balance will be like this. Here the oil is coming in. Now, only there is a flow, then there will be pressure drop. So, we can calculate what will be the pressure drop here. Very quickly I am showing this. Return spring force and the flow force balance the net force due to the pressure difference. what is there, this PC is less than PS. So, PC into this area, the area is same, because the thrust area is same, this poppet area and here the poppet area, but there will be definitely this some difference that is balanced by the spring. So, when at point when the PC reduces, then definitely force here will be more than this and then this will open. But while it is opening, the spring is being constant and at one point it will balance the force. So, according to the main stage force, we can write down these equations and we can, the pressure force F PRM is given by this is the area and this is the pressure here and this is the area there and the PC is the pressure here. This pressure is actually this AS, although it is written like this, but AS is the full pressure here over the whole area. It is not only acting over here, it is also acting over there. So, AS and ASY it might be same, but this we have kept separately because if there is any differences. Because when it is closed, it might be this area is less than this. So, you can use this formula, and steady state flow force is already expressed in equation 12 earlier, and the poppet opening YS main stage spring force FSM having an initial compression of YS0 is 2.5 into 10 to the power minus 3 is expressed as, now this is for a specific value, of course we have used this formula. So, in that way we can estimate what is the force balance, everything we can calculate. Now, this is only we have how we can estimate the orifice characteristics, force balance equation, all such thing, flow force, everything we have calculated. Next day we will continue that how the performance is achieved, or this the purpose of this analysis is that not only to understand the performance, but also to understand the design of such valve. Now, this is definitely in the note you will find, or this so many references. If you are interested, you have to go through few of such references. Thank you.